Chapter 5, Basic High-Angle Hardware. In this presentation, we'll discuss the impact of hardware on the high-angle system, describe types of carabiners, describe the types of descenders, rope grabs, and other hardware used for anchoring. We'll identify hardware used in belay systems. We'll identify the hardware used in belay systems. We'll describe the use of pulleys in high-angle activities. We'll talk about the role of rigging plates and swivels as well as edge rollers. Rope, webbing, and other software are critical to the high-angle system. However, another vital link in the system is the category of equipment known as hardware. Hardware includes a variety of gear, usually constructed of metal, that performs specific functions in the high-angle environment. One of the most elemental and basic hardware components of a rope system is the carabiner. Carabiners are metal connectors that link the elements of the high-angle system. They are also sometimes called beaners, snap links, or crabs. The basic parts of a carabiner are the spine, the hinge, the gate, the nose, and the latch. Depending on the manufacturer, carabiner latches are designed in a variety of ways. There are three basic types of carabiner latches. The pin and slot. The pin is in the top of the gate and engages the nose when closed. The claw and slot, in figure B here, the nose of the beaner is a claw shape that engages a slot on the gate. And number C, the key lock. The nose of the beaner has a distinct shape with no cutouts. This then engages the matching slot in the gate of the beaner. All carabiners have their max rating when properly loaded and when the gate is completely closed and locked. Carabiners are manufactured in a wide variety of shapes and usually are designed for specific uses. They were originally designed as a simple oval shape, as we see in figure A there. When an oval carabiner is placed under load, the stress is the same on both sides, meaning stress is placed equally on the spine and the gate. This is a problem because in any carabiner, the weakest side is the one with the gate. So the design that takes greatest advantage of the strength of the spine is the D-shaped carabiner in figure B. So as we can see, the spine side of the carabiner is longer than the gate side. The top and bottom of the carabiner flares towards the spine. The purpose of this design is that when under load, a rope or similar material clipped into the carabiner will slip into position on the spine side, and as a result, greater stress is put on the stronger side of the carabiner. Since the development of the D carabiner, other designs have been produced, such as the modified D and the HMS or Halbmasterung carabiner, which is pear-shaped carabiner designed for use with the Munter hitch. Because climbers must carry their equipment with them, carabiners made primarily for rock climbers tend to be lightweight. Some are constructed of hollow aluminum. They have low strength ratings, and carabiners need higher strength ratings for more demanding use. Higher strength is essential for when more than one person's body weight may be involved, such as in rescue situations. Such types are made of solid aluminum or steel. Here we have a lightweight oval non-locking carabiner in the top left. On the bottom there we have what they call a wire gate climbing carabiner, and then to the right of the slide we have the tried and true classic NFPA steel locking G-rated carabiner. Carabiners also differ in size. Climbers place a premium on weight and bulk, so their carabiners tend to be relatively small. However, they need to be larger for situations such as rope rescue activities. The carabiner gate opening. In carabiners, there are differences in the widths of the gate openings. For some activities, the carabiner gate opening must be larger. For example, for rescue situations, the carabiner gate opening must be larger so it can be clipped over a litter rail, which can be as large as 1 inch in diameter. On this slide, these are both NFPA rated carabiners. However, notice how the gate design to the left allows for a wider gate opening when compared to the one on the right. The main job of a carabiner is to maintain its link with the other elements of the high-angle system. The carabiner gate must remain securely closed. Otherwise, the connecting elements can come unlinked and the system will fail. Carabiners can accidentally become open during rope rescue operations. Here are two examples of conditions that could cause an accidental opening of a carabiner. The one to the left, the carabiner is pressed against the edge of a wall or rock, forcing the gate open. A rope or a piece of webbing on the right is pulled across the carabiner gate, forcing it open. In these two examples, we can see the first bad decision was the choice of a non-locking carabiner. Secondly, our job as rope rescue technicians is to think ahead of the problem and identify these situations and develop a solution before we have an issue. For the most part, in the rescue world, we should never rely on non-locking carabiners for several reasons. However, the most important is that they will not have the required strength to achieve our preferred safety margins. However, if you have no other choice, when using non-locking carabiners, two carabiners should be set together, reversed, and opposed to prevent the gate from accidentally opening. In other words, the pair of carabiners should be set with their gates reversed to one another and their tops and bottoms opposed to one another. Together, reversed, opposed. So instead of non-locking carabiners, we prefer to use locking style carabiners. Using a single locking carabiner often is quicker and more convenient than using two reverse and opposed carabiners. Although specific designs vary with the manufacturers, locking carabiners usually fall into the following categories. To the left is a screw lock carabiner. A locking sleeve moves on a screw threads over the nose of the carabiner to ensure closure. A sleeve turns around a pin on the gate to move up and closes over the nose. So on the right is an auto lock. A spring-loaded sleeve called an auto lock could be a manual locking sleeve, requires a quarter turn to unlock. It should be used with caution because some versions can open very easily. Notice the padlock icon is visible when the gate is locked. An unlocked padlock or a skull and crossbones is visible when the gate is unlocked. As with everything we use today, some carabiners are not as strong as advertised, especially when the locking knob is in the unlocked position. For these designs, the locking knob must hold the claw-type latch together in the lock position to have its full rated strength. Tests have shown that some designs can fail if the gate is unlocked. Carabiners are subject to fail when they are overloaded, whether the gate is closed and locked. Again, as technicians, it is your job to use the right tool at the right time. In addition to the long axis lock strength of a carabiner, you should know its long axis unlock strength, long axis gate open strength, short axis or gate cross-loaded strength. Certified carabiners should be labeled to give you the information, as we can see from the example on this slide. Whatever type of carabiner is used, those using it are responsible for constantly making certain that the carabiner gate stays closed. If a carabiner chronically becomes unlocked without apparent cause, it should be retired from service. Older design carabiners could become jammed if the locking knob is over-tightened. Newer designs have a gap between the sleeve on the gate and the nose of the frame when the sleeve is screwed completely closed. To check to see if a carabiner is a new design type, screw it all the way closed, and slight amount of play should remain in the gate. Almost got it. If you do have a carabiner that will not unlock and it is the screw lock type, first move to a safe place, then load the carabiner with your body weight. When it's under load, it may loosen up. Avoid using tools to tighten gates and limit tool use when trying to free a stuck screw lock. This can damage the carabiner, the gate, as well as the lock. Steel versus aluminum. Carabiner construction. Advantages of aluminum alloy are it is significantly lighter weight, it's less expensive than steel, and it doesn't rust. The disadvantages of aluminum are that the locking mechanism on some aluminum designs eventually may wear out, severe shock loading may cause permanent damage, and some aluminum carabiners are not as strong as comparable steel designs. Advantages of steel carabiners are the locking mechanism on some steel carabiners may hold up better than the locking mechanism on aluminum carabiners. Steel carabiners may hold up better under severe shock loading. However, steel is heavier than aluminum, and they are more expensive than aluminum types. Unless plated, steel will rust, so consequently, most steel carabiners require more maintenance than the aluminum. Currently, 3 labeling systems are used for carabiners sold in the United States: the European Committee for Standardization and the Union of International Alpine Association Systems, which is CEN and UIAA. Also, we have carabiners certified by the National Fire Protection Association, NFPA, and then the National American Standard Institute, or ANSI. The CEN or UIAA system, carabiners that pass the CEN and UIAA standards are labeled with specific markings. These carabiners are stamped with major axis, minor axis, and gate opening strengths, which are shown in kilonewtons, KN. A newton is a unit of force measurement, and 1 newton equals about 0.225 pounds per foot. 1 kilonewton, or 1,000 newtons, equals about 225 pounds. Just remember that. 1 kilonewton equals 225 pounds. The NFPA system carabiners that meet NFPA 1983, Standard on Life Safety Rope and Equipment for Emergency Services, also carry special markings and are marked with meets NFPA 1983. At this point, I believe it's 2016 edition. They carry the name or logo of the manufacturer along with the label or third that certifies the product meets the standard. NFPA certified carabiners also have either a T or a G stamped into the frame. The letter T, as in Tom, indicates that the carabiner is for technical users and designed for lower loads, or for when actual system loading is unacceptable for a T carabiner with a major axis minimum braking strength with gate closed of 27 kilonewtons or 6,075 pounds. The letter G, as in George, indicates that the carabiner is for general use rescue with a minimum major axis braking strength with gate closed of 40 kilonewtons or 9,000 pounds. Note that in past editions of NFPA 1983, the T rating was known as L or lightweight. Remember these ratings throughout the course because they will be very similar when discussing other types of rope and rope equipment. ANSI is an organization that oversees the development and implementation of voluntary consensus standards relating to products, processes, systems, and personnel that involve businesses in the United States. ANSI also coordinates with other standard-setting organizations worldwide. For high-angle rope activities, ANSI standards apply for industrial workers in areas such as fall protection and rope access. Carabiner use. A carabiner's manner of function is to be loaded along its long axis or lengthwise. As mentioned earlier, the weakest point of a carabiner is the gate. Consequently, side loading stresses the gate and puts an unnatural force on the carabiner, which severely reduces its strength and may cause it to fail. So figure A identifies the stress and suggested configuration of a carabiner. We can readily identify the gate load in figure B and correct it before we load the system, but we often overlook the situation represented in example C. This situation is very common and often overlooked by rescuers. It appears to be rigged appropriately, but with further inspection, we see that the forces are placed along the short axis or the gate side of the carabiner, which, as we have discussed, is often a weakest side. The same situation occurs when we use webbing that is too big to sit in the carabiner appropriately. We, as rescuers and technicians, are responsible for identifying these situations and correcting them. In this slide, we see an anchor system that we see quite frequently. Looks pretty good, but if we look closer, we can see that we're loading the carabiner inefficiently and placing a good portion of the force on the gate side. When a load is placed on this anchor, we will load it in all 3 axes, also known as triaxial or 3-way loading. And as we will learn, will cause the carabiner to function in a manner that was not intended to be used, and because of that, it could fail. Failure is always bad in the rope rescue environment. In this slide, we see the same anchors, but a different configuration. As we go through the class, we will learn to change the way we rig to anchors to improve system performance. In this example, we notice that the carabiners are now loaded on their long axis, and when a load is applied, the force will be placed on the long axis, and therefore it will create a much stronger anchor system. Hard linking. Another possible cause of carabiner failure is hard linking. This occurs when a carabiner is rigged so that it cannot rotate with the forces placed on it. This twisting force can cause the carabiner to break. To avoid hard linking, rig a soft link such as a section of webbing or rope between the hard links. Here we have a carabiner hooked directly to another carabiner. If this system rotates and there's no relief, it can break or significantly damage the carabiner. On the right, we see a picture of a carabiner that was damaged by rotational force. It does not appear to have broken, but it is significantly damaged and could have failed. To avoid hard linking, rig a soft link, such as a section of webbing or rope, between the hard links. In this slide, we see a few examples of how to avoid the hard link. The slide to the left is a system called a quick draw. Designed for rock climbers, it has a soft interlink between the carabiners to avoid hard linking. It also provides some other benefits for climbers which are not discussed in this course. The slide to the right shows the use of rope as a soft interlink between carabiners. What else does the slide on the right depict? If you said to yourself that these carabiners are reversed, opposed, and opposite, you're correct. Never use a carabiner as a descent control or brake bar in the rescue environment. This system is usually for recreational climbing or for emergency self-rescue. Brake bars are solid bars of metal with a hole drilled in one end and a slot cut on the other. They sometimes are fitted to oval carabiners to create rappel systems and occasionally lowering systems. Because they subject carabiners to forces for which they were not designed, carabiner brake bar systems should be avoided. Carabiner brake bar systems are not as common as they once were, but are still used by some in the high-angle environment. Another issue that is common with the use of carabiners is three-way or triaxial loading. Carabiners are designed for loading along the long axis. Triaxial loading can occur in seat harness attachments, anchors, and just about everywhere else we have three legs or attachment points. This can place potentially dangerous side loading forces on the gate. Screw links. These are triangular or semicircular screw links. Increasingly are being used in place of carabiners when three-way loading is necessary or anticipated. Instead of the swing open gate found on carabiners, screw links have a screw locking sleeve that manually closes the opening. When the screw link is screwed closed completely, it has the same strength regardless of the direction or directions of loading. As with carabiners, users of screw links should avoid side loading. It can stress the gate, puts an unnatural force on the screw link, and severely reduces its strength, possibly causing failure. However, the advantages of a screw link: they're inexpensive, they retain their strength regardless of direction of loading. They're also smaller than carabiners, so they take up less space. The big disadvantage is that they must be manually screwed closed to be safe and all the way closed for strength. Another disadvantage is they can take time to open and close, so it's not as fast as a carabiner. Care and inspection of your carabiners. You must inspect each carabiner after use. Check the gate for signs of excessive side loading, such as rough pivoting action and bent parts. Pay particular attention to hinge pins and latches. Make sure that what may look like a scratch is not actually a crack. A deep gouge scratch in a carabiner can reduce the cross-sectional area needed for strength. Scratches also can provide an entry point for corrosion. Corrosion is particularly critical in hinge pins, latches, springs, and locking knobs. If your carabiners have gotten wet, dry them in a warm place. Use a preservative and lubricant such as LPS1 on critical areas such as hinge pins, spring latches, and locking knobs to help prevent corrosion. Wipe off excess lubricant before storing the carabiners. So here, Table 5.2 identifies some common problems and solutions for your carabiners. This is in your book, so you can review this at your leisure. Descenders, also generally called rappel devices or braking devices. So there are a lot of different kinds, but they all operate on the same principles. Some of the same equipment can be used as braking devices to lower people or equipment under control. Such lowering operations may be required during rescue activities. Although many different descenders are available, they all work on the same principle. The descender creates friction with the rope running through it to produce a controlled descent, and in most cases, the user controls the speed of the descent by pulling on the section of rope below the descender to create more friction. Here we have the figure 8 descender. It's a one-person rappel device roughly shaped like the numeral 8 but with rings of unequal size. The smaller ring is clipped into a seat harness with a carabiner or screw link. The larger ring is the one through which the rope passes to create the friction. All are made of metal. Most are made of machined or forged aluminum alloy that is anodized for greater resistance to wear from the rope, and some are constructed of steel. The advantages of steel models more resistant to wear, and they are particularly appropriate for heavy-duty uses such as those seen in training departments. Disadvantages of steel: they're heavier in weight and they can cost more, and overall they generate less friction. Figure 8s come in a variety of shapes and sizes. They are also a very common used for rappel devices and are relatively inexpensive compared with some more complicated pieces of equipment. The disadvantage of a figure 8 descenders is that with most models, once on the rope, the repeller cannot create a wide range of friction in the device. And with all models, long rappels, more than about 150 feet, should not be done because they become difficult to control. The conventional figure 8 descenders are mostly found in smaller sizes. They typically have a rounded or slightly squared large ring, used primarily in the recreational activities. However, for many years, the figure 8 was the go-to rappel and descent control of choice for rope rescue. Only after the advent of other devices did the figure 8 favor. That being said, there are still some uses for the figure 8 in rope rescue work. The big disadvantages are all models twist the rope. In long rappels, you can twist the rope so much that you will stop your descent and be stuck. This twisting action can also ruin your rope. In conventional models, the rope can slip around the large ring to form a girth hitch, like we see here in this slide. If this happens during a rappel, the user may be trapped on the rope, and this can be a difficult situation for which to extricate yourself. Again, the twisting action created by the figure 8 aids in the formation of this girth hitch. In this slide, we see a picture of the figure 8 descender with ears. The ears in this device are projections fabricated into the large ring. These devices are sometimes called rescue 8s. They are specifically designed so that the rope contours better around the large ring and does not slip over it to form a girth hitch. This type of figure 8 is found in larger sizes. The advantage of the figure 8 descender with ears is primarily that the rope is less likely to slip around the large ring and form a girth hitch. Most models are available in larger sizes, which dissipate heat better, and these types of descenders accept larger ropes. Disadvantage of the figure 8 with ears is that they twist rope. They are more difficult to control on long rappels, and once on the rope, they can create a wide range of friction. So all the problems with the figure 8 enter the bar rack. Also called a coal rack or rappel rack, it's a descending device that offers a great amount of control and the ability to vary greatly the amount of friction. It also can be used for very long rappels. The brake bar rack consists of two primary elements. The first element is a frame, and there are two designs. The U rack because it's shaped like a U, and a J rack because it's shaped like a J. Most frames are made of stainless steel or aluminum. The second element is a series of bars with a hole drilled in one end so that the bars slide freely on the long side of the frame. On the opposite end, the bars are notched so that the end of the bar can clip into the short side of the frame. The rope is woven through the bars, and under tension, the rope keeps the bars in place on the frame, and the bars must be loaded in the correct sequence for safe operation of the device. In the most common configuration, the rack is arranged with a 1-inch diameter top bar. On J racks, this top bar may be grooved to keep the rope in the middle of the bars as it runs through the device. On a U rack, the second bar down is often grooved. The remainder of the rack usually is filled out with 5 aluminum bars, each 7/8 inch thick in diameter. The device works by creating friction either by the use of the brake hand positioned below the rack or by bar spacing on the rack itself manipulated by the control hand. Many people, when they are first exposed to the bar rack, want to control the friction by removing bars. This is an excellent way to injure yourself and others. First, we learn about the device and understand how bar spacing and brake hand manipulation is used appropriately. And once we understand how the device works and how we can control it, often we find that the removal of bars is not needed. The tie-off bar or hyper bar is just a fancy name for a larger bar with an ear. It can make hard locking the device easier, but is not needed. With some practice, you'll have no problem tying off in any type of rack. Like any other piece of equipment, the bar rack comes in different styles and sizes. In rescue work, we're not overly concerned with weight and size. Unless you're on a search and rescue team that will be hiking everything in, don't get hung up on size and weight. The most important factor in our equipment is understanding what it can do and what it cannot do, how much weight and force it can and cannot handle. There are other types of descenders out there. You'll be exposed to several of them through the class. However, your primary descent control during class will most likely be a rack bar for several reasons. 1, it's a very common piece of equipment. 2, it's very cost effective. And 3, it works well. On this slide, we have a couple different descenders, the Petzl ID, the CMC MPD or multi-purpose device, which is gaining popularity, and then to the far right, looks like an ID, but it's a Petzl rig. And if you don't understand the differences between the two, it could be a real bad day for you. Rope grabs. Rope grabs are devices that grip the rope and have a variety of uses in the high angle environment. In this text, the term rope grab refers to a device used for personal safety, also referred to as a QAS, quick attachment safety, ascending the rope, used in hauling systems. In industry and construction, some types of rope grabs are also used for personal protection against falls. Many rope grabs are mechanical devices made of metal that use a camming action to grip the rope, sometimes called hard cams. Rope grabs can also be made of rope or webbing formed into a hitch that grips the rope, sometimes called soft cams. Hard cams. Here we see two of the most common types of hard cams used in rope rescue. On the left is the Gibbs or general use ascender, and on the right is a handled or technical use ascender. Both operate as a cam, meaning that when force is applied, they grab the rope. They are directional use devices, meaning they are designed to travel in a specified direction and grabbed in the opposing direction. The most often used soft cam is the Prusik. There are other hitches and loops used as soft cams, but the Prusik will be our primary focus. The Prusik will be used in mechanical advantage systems as well as ascending and personal safety. Technical use ascenders, also called personal ascent devices, handled ascenders, are rope grab devices used to travel up or ascend a fixed rope. They all work on the same principle. If the ascender is correctly attached to the rope, its gripping action allows the climber to slide it freely in one direction, usually up. The descender then locks in place when the climber correctly applies a downward force, for example, your body weight, to it. Many technical use ascenders have a handle equipped with a safety catch, which releases the cam so that the ascender can be placed on a rope with only one hand. Many technical use ascenders are used in pairs, usually with right and left-handed models. Most technical use ascenders cannot be used on ropes larger than ½ inch or 12.7 millimeters. Technical use ascenders are designed for ascending with only one person's body weight and are not for hauling systems in which forces are multiplied. Please take note of the red circle on the right. The technical ascender has sharp points that grab the rope and the cam. This is usually not destructive for single-person loads. However, with multiple-person loads or in a mechanical advantage system, they can damage the rope significantly. The general use ascender, these are rope grab devices designed for use with heavier loads than those used with the technical use ascenders. They may be used as personal ascenders, but many models are less user-friendly for personal climbing systems. More typically serve in hauling systems as progress capture devices and rope grabs, and most do not have handles. Often referred to as a Gibbs ascender because that's who makes it, and that's what many people know it as. Initially, you may find general use ascenders a little more difficult to operate than other types of ascenders because they must be taken apart to be placed on the rope. However, once they've been assembled on the rope, they tend to stay there. They tend to hold better than other types of ascenders on wet, muddy, or icy ropes as well. Take note of the cam that's been circled in red. The teeth on the cams are designed to hold well on the rope while causing a minimum of damage to the rope sheath. Compare these teeth with those of a technical use ascender, and you will notice that they're not sharp and pointy. Because of this, they tend to do less damage to a rope under tension or in mechanical advantage systems. However, under very high loads or severe shock loading, any general use ascender may damage the rope. Artificial anchors constitute a family of hardware used to create anchors where no natural anchors are available around which rope or webbing can be placed. Artificial anchors go directly into the rock and in some cases into ice or snow. Most often they are placed in cracks or gaps in the rock. However, in some cases they are physically driven into the rock to act as permanent emplacements. The ability to place reliable artificial anchors is an art involving a number of subtleties, such as the character of the rock itself, the nature of the cracks or gaps in the rock, and the direction of loading on the anchor. This kind of knowledge depends very much on hands-on instruction and experiences and is beyond the scope of this text. These are not primary anchor devices for rope rescue. The importance of these devices are informational. You may need to rescue someone who has used these devices for an anchor, and you will need to evaluate their use and stability. Bolts are a means of establishing a permanent anchor in a wall, usually when no other anchors are feasible. Although different designs of bolts are available, most work on the same principle. A hole is made in the rock with either a separate drill or in some designs with a drill that uses part of the bolt as the bit. The bolt is set in the hole by causing an element in it to expand, either through a screw-like action or by hammering on the bolt. Some bolting systems use glues for greater security. A hanger is attached to the bolt. A carabiner can be attached to the hanger, and for strength and long life, all bolts and components should be made of stainless steel. Note that the CEN standard on bolts requires that they be made of stainless steel. Bolts are used in rescue. Primarily, you will see them used in lifting and moving operations, such as crane operations. Other types of anchoring hardware have been developed, partly because bolts deface the rock. Initially, these other types were known collectively as clean hardware. Although clean hardware generally does not deface rock, it may not be as secure as bolts. Among the basic types of clean hardware for anchoring are nuts, chocks, or stoppers, which work by being wedged into a rock crack that bottlenecks. Here on this slide is an example of a nut or a stopper anchor. It is wedged into the crack and downward pressure is placed on the anchor wedges itself into the crack. And as long as the anchor has tension on it, the stopper holds. However, when tension is removed from the anchor, there's the possibility of the anchor letting go. Other types of clean hardware include hexcentrics, which work by both a wedging and cam action. We see that in the top left of the slide. And then a spring-loaded camming device works by a spring-loaded or opposed cam action. Belaying is protecting a person from falling by controlling an unloaded rope, the belay rope, in a way that secures the person on the rope in case that individual's mainline rope or support fails. The technique shown here is a one-person belay. This would not be an acceptable belay procedure for rescue activities. It's important to know the differences between belaying one person versus belaying a rescue load. Many devices and techniques that can be used for belaying one person are not adequate for belaying a rescue load. NFPA 1983 includes belay devices in section 7.15. Belay device performance requirements divides them into two categories: technical use belay devices and general use belay devices. In a one-person belay, the belay rope is attached to the person being belayed and is controlled by the belayer. The difference in belaying technique relates mainly to the manner in which the rope is held or belayed. As this black and white hand drawing depicts, the oldest belay technique is the body belay. The body belay involves running the belay rope around the body of the belayer, usually around the waist. In this way, the rope can be brought tight if the person on the end of the rope fails. In this way, the rope can be brought tight if the person on the end of the rope falls. The rope is held by friction around the belayer's body. Body belaying has significant disadvantages. The force of the fall may cause the belayer to lose control of the rope and drop the climber. The force of the fall can easily injure the belayer. The belayer can become entangled in the rope, and if the belayer does not catch the climber, he or she must hold the individual so the climber can become secure. Because of these problems, alternatives to body belaying have been developed and are preferable. We will demonstrate a form of body belaying called bottom belaying, where the climber is rappelling with a rack bar. Belay devices are equipment used to belay a person exposed to falling. In most belay devices, a bight of rope is fed through the unit. One end of the rope goes to the climber or person who may fall, and the other end of the rope is controlled by the belayer. There are many different tools available to belay. Regardless of the tool or method used, it is imperative that the user be adequately trained in the system used properly. From left to right, we have the ATC, or the air traffic controller. This is a lightweight belay device. It's a personal belay device and is considered a belay plate. The center is the Gree by Petzl, which is a cam-actuated belay device, and then the figure 8, which can be used effectively as a belay device as well as a descent control. The Munter hitch, or Italian hitch, is another system for belaying. It requires only a large locking carabiner like the Halfmaßwasserschwung or the HMS, something to anchor it to, and a rope. When properly tied and operated, the Munter hitches can work as personal belay systems for falls with a low fall factor, but not with large loads or high fall factors. The ability to catch a load with the Munter hitch varies depending on the rigging situation. If more than one person is on the load, the potential load can be mitigated by rigging separate belays so that only one person ends up on each Munter hitch belay. No belay device or technique is perfect for all rescue loads and in every rescue environment. Great caution must be exercised in choosing any belay device for rescue loads. Before you put the device to use, test it under realistic conditions that you will encounter in your own rescues. The Tandem Prusik belay is often used in rope rescue as a belay device for multiple person loads. It consists of 2 Prusik hitches, one short and one long. To operate, the Prusik are anchored to an appropriate anchor for the load and minded by the belayer. If a fall occurs, all the belayer has to do is drop the barrel knots and the Prusik will grab the rope abruptly, stopping the unplanned descent. We will cover belaying equipment and techniques as the class goes on. These last few slides were simply an introduction. Although a pulley is designed primarily to reduce rope friction, this capability makes it useful in a number of functions in the high-angle environment. Pulleys also can be used to change the direction of a running rope, position a rope more conveniently, reduce abrasion on a rope, and to develop a mechanical advantage in a hauling system. When life safety activities are involved, only all metal pulleys should be used. As with other auxiliary equipment, NFPA 1983 classifies pulleys as either T for technical or G for general use. Here we see several uses of pulleys in a system. Right above the rescuer, this pulley here is what we call a COD, or change of direction pulley. And then in the load system itself, we have working pulleys that create the mechanical advantage as they move. The following are other important characteristics of pulleys used in high-angle work. Ideally, the sheave, or the wheel, should have a diameter of at least 4 times the diameter of the rope. This is also known as the 4-to-1 rule. So, for half-inch rope, which is typically used in rope rescue, the pulleys must be at a minimum 2 inches in diameter. Side plates should be movable so that the pulley can be placed on the rope anywhere along its length without the end of the rope having to be fed through the pulley. If rope abrasion is a concern, pulleys with side plates that extend beyond the edge of the sheave far enough to protect the rope should be used. The side plates generally are the weakest part of the pulley. Therefore, pulleys for higher tensile strength rope, larger than ½ inch, should have stronger side plates. Pound for pound, steel side plates are stronger than those made of aluminum. Axles should have rounded bolt heads that will not snag rope, other gear, or the rock. Most pulleys for high-angle work have one of 2 types of bearings, either bronze bushing or a ball bearing. Bronze bushing pulleys are very strong. They can be taken apart to be cleaned. They're less expensive than a ball bearing, but can also be contaminated by dirt and grit. In contrast, the ball bearing pulleys turn slightly more freely. Some are sealed to prevent contamination by dirt and grit. However, they are slightly more expensive, and they do not take stress such as sudden blows as well as the bronze bushings. Ball bearing pulleys are also damaged when the hardened steel balls dent the bearing races, and this is technically called brittling. A number of pulleys for the high-angle environment have been designed for specific tasks. One of these is the knot-passing pulley, also known as a kootenai. The large sheave on this type of pulley is designed so that the knots connecting lengths of ropes can pass over it easily. They are also used in MCP or movable control point operations like highlines and swift water rescue MCP operations. One other note on the kootenai is not only will it pass a knot, we can run 2 lines through it. So again, in a high line, if we're going to do a double line for our track line, the kootenai can actually pass 2 ropes simultaneously side by side. Rigging plates serve as collection points for multiple anchors and or rigging points. They help keep anchor rigging organized and can save time in setting anchors. They come in a wide variety of shapes and sizes. They're usually made of aluminum, but steel plates are available. They're also certified through one of the many certifying agencies. NFPA does certify plates both at T and G ratings. Swivels are placed in rope systems where torque may be present. They help prevent rope and equipment entanglements. They're sometimes used in helicopter short-haul systems to reduce spin. Remember our discussion in hard linking? Swivels may be an option to interface between 2 hard links. It is a metal connector, but it allows for rotation without binding. Edge rollers can be important devices for reducing the friction generated by rope going over an edge. They can be made of material that moves, like edge rollers, or they can be static and provide only a smooth surface to limit rope damage over an edge. In this slide, we can see several types of edge rollers. Also pictured is the Bourne Entry Ease. This device is very useful as edge protection as well as confined space entry. One important note on edge rollers and edge protection: you must secure the edge protection device. As the rope moves up and down over these devices, the rope and the friction can move the device. If they're not secured, they can fall or shift, causing serious injury or significant rope damage. So in summary, hardware includes a variety of gear, usually constructed of metal, that performs specific functions in the high-angle environment. Carabiners are metal connectors that link the elements of the high-angle system, the basic parts of the spine, the hinge, the gate, the nose, and the latch. Carabiners are manufactured in a wide variety of shapes and usually are designed for specific uses. Carabiners made primarily for rock climbers tend to be lightweight, and for more demanding use and when more than one person's body weight may be involved, such as in a rescue, carabiners need higher strength ratings. For some activities, such as rescues, the carabiner gate opening must be larger. Although 2 reverse and opposed carabiners usually are very secure, using a single locking carabiner often is quicker and more convenient. For the most part, carabiners are made of one of 2 metals, aluminum alloy or steel. Currently, 3 labeling systems are used for carabiners sold in the United States: CEN, UIAA, the NFPA, and ANSI. A carabiner's manner of function is to be loaded along its long axis or lengthwise. A possible cause of carabiner failure is hard linking, which is when a carabiner is rigged so that it cannot rotate with the forces placed on it. To avoid cross-loading, you should avoid using carabiner brake bar systems. Some seat harness designs have tie-in points consisting of a right and left attachment. A carabiner clipped into these attachments and then loaded through a rope to a descender or other point becomes loaded in 3 directions, or triaxial loaded. Triangular or semicircular screw links increasingly are being used in place of carabiners when 3-way loading is necessary. You must inspect each carabiner after use. Descenders, also generally called rappel devices, are braking devices. A brake bar rack is a descending device that offers a great amount of control and the ability to vary greatly the amount of friction. With all gear you use in the high-angle environment, it is your responsibility to obtain specific information about the characteristics of each device and how to train in its use. All right, that does it for this chapter.